Good afternoon. In case I'm not back from my jab, here's a short video to replace the live video lesson that we'd otherwise have. Now, if I switch cameras to the iPad, just a sec, today we're going to be looking at one or two friction problems. Now, I'm pleased to say that we do have the textbooks to give out to you when you're back in school tomorrow. Unfortunately, we haven't yet managed to sort out the online textbooks. There's an issue where we've had to go back to dynamic learning to sort out some technical problems. Anyway, today we're going to look at some questions from Chapter 3. And as soon as we can give you the textbooks tomorrow, I'm going to be able to set you a mixture of questions from chapters 1, 2 and 3. All of these basically go over the A-level content that we've covered already, and there isn't really anything new within it conceptually. It's just these problems are a little bit harder than some of the ones that we've looked at within single maths. So if within the friction OneNote you scroll down to just below the notes from the PowerPoint, all these PowerPoint notes are examples we went through in the first half of this term. You'll see this question, a box of weight 200 newtons pulled at a steady speed across a rough surface by a rope, and there's a tension T in the rope, and we're told the coefficient of friction is 0.5, and if the box slides without tipping, two things we've got to find: an expression for the tension in terms of the angle, and we've got to find for what value of alpha the tension force will be a minimum. So the first thing to do, as always, is to add in the other forces, and they're going to be the weight of the box, which we're told is 200 newtons, and the other forces that we're going to have will include a normal reaction force and a friction force which must oppose motion, so acts to the left, and then with the tension force at an angle alpha to the horizontal, we split it into a horizontal component of T cos alpha and a vertical component of T sine alpha. And now we can form some equations by resolving, and we're told that the object is moving at constant speed, and that means that the forces will have to balance both horizontally and vertically. So vertically first, if the upward force equals the downward force, we're going to get that R plus T sine alpha, the upward force, has to equal 200 the downward force. Then horizontally, force to the left equals force to the right, F equals T cos alpha. And finally, we can say that because the object is moving, friction must equal its maximum value of mu r, and mu, it tells us in the question, is 0.5, so we're going to have F equals 0.5 r. So those are our three equations from resolving horizontally, vertically, and applying F equals mu r. And now we have to solve them simultaneously, and we need to get T just in terms of alpha. So that is going to mean eliminating the other two letters, f and r, between the equations. So if we want to do this, we'll have to substitute. So for f, we could begin by writing 0.5r equals t cos alpha, subbing for f from the bottom equation. And now, if we use the top equation, one way of doing this might be to make r the subject. So r is equal to 200 minus t sine alpha, and now sub this expression for r in the equation below, and it would become 0.5 times 200 minus t sine alpha equals t cos alpha, and timesing out the bracket, we'd end up with 100 minus t over 2 sine alpha equals t cos alpha. And we need to make t the subject, so we need the two terms containing t on the same side. So if we add this term to the other side and then take out t as a common factor, we'd have t bracket cos alpha plus a half sine alpha. So then t in terms of alpha, divide through by the bracket, and we get t is equal to 100 over cos alpha plus half sine alpha. And if you don't want any fractions within the expression, then we can times through by 2 on top and bottom, and we could write it as 200 over 2 cos alpha plus sine alpha. And that completes part 1. And now for part 2, find the value of alpha for which t is a minimum. So in this case, what we're going to have to do is minimize this function. Now, if we notice, alpha only appears in the denominator of the expression. That means that if we write f of alpha as 2 cos alpha plus sine alpha, if we're trying to make the whole expression a minimum, we would be making the denominator a maximum. And to maximize a function, you would differentiate and put equal to 0. So when you differentiate cos alpha, you get minus sine alpha. And when you differentiate sine, that goes to cos. Put equal to 0, and then this would turn into 2 sine alpha equals cos alpha. In other words, sine alpha over cos alpha, or tan alpha, equals a half. And then if on your calculator you tap in inverse tan of a half, you would get 26.6 degrees. And finally, what is the value of that minimum? So if alpha is an angle whose tan equals a half, that's sine, so tan is opposite over adjacent, equal to a half, then the length of the hypotenuse, square root of 2 squared plus 1 squared, is root 5, and that means that the value of sine alpha, opposite over hypotenuse, is 1 over root 5, and the value of cos alpha, adjacent over hypotenuse, is equal to 2 over root 5. So if we now substitute these values of cos alpha and sine alpha back into the expression, we end up with 200 over 2 times 2 over root 5, so that turns into 4 over root 5 plus sine alpha 1 over root 5, and simplifying the surds, working in exact form, the denominator is 5 over root 5, so we're going to end up with 200 over 5 is 40, and dividing by 1 over root 5 is equivalent to multiplying by root 5, so we end up with 40 root 5 in exact form for the minimum value of the tension. Now, this gives you an example of a slightly more involved further maths problem on this same topic. You will see, scrolling down, that there are 3 more such problems which combine the familiar principles of resolving an f equals mu r with a little bit more involved pure maths trigonometry. I'd like you to have a go at these three questions. If you can have a go for Wednesday, and I will circulate to you by PDF, in PDF form, the solutions that you can check, and I'll be able, hopefully, to give the textbooks out to you tomorrow morning in morning registration. I know that going a week without the textbook that I was about to give out is less than ideal, but we're not going to have to carry on like this for much longer. Anyway, looking forward to seeing you all tomorrow morning. Okay, bye for now.